by 6, or your odds ratio you calculate from this table, is statistically significant. And to do that, we need to compare this table to another table, a table we'd expect to see if everybody had the same risk of needing a vacation. We had 21 people who completed the survey. 11 of them said they needed a vacation now. That's 52.38%. The null hypothesis said that everyone should have that same risk of 52%, rather than 45% among the spam users and 60% among the non-spam users. The null hypothesis says there's one single risk, regardless whether you eat spam or not eat spam. From that, we can generate another table. This is the expected table. So if 11 people were eating spam, they all had a risk of 52.38%, we'd expect 5.78 of them to say they need a vacation right now. We had 10 other people who were in the non-spam group, but they also had the same null risk of 52% of needing a vacation now. We would expect 5.2 of them to report needing a vacation. So the test of significance is going to compare the observed table, this expected table, using that calculation to calculate x squared. Get a small value, 0.4443. And you say, is this a typical value for a test statistic like this when the null hypothesis is true? Small values would support the null hypothesis, large values would not. What you do is you look this number, 0.4443, up in a table of values from a chi-squared distribution with 1 degree of freedom to see if 0.44 is a typical value. Well, it turns out in that table, half of the values, 50.5051, were bigger than 0.4043. So this is a typical value. It occurs, values like this or larger occur half the time. So these data do support the null hypothesis. The p-value is not statistically significant at the 0.05 level, because it's much larger, 0.50. So this is a generic approach of how we do test of significance. And it's specific when we have a binary outcome and a binary risk factor. So if you ran your data through SAS, this is part of the output you have. It says here are the statistics for the table we just looked at. It does a chi-squared test for you. It says the test statistic value is 0.444. P-value is 0.5051. Gives you a bunch of other values, all called chi-squares, and the values are somewhat similar. One's a little bit different, but 3 of them are all around 0.5. And all that means is there are different ways to analyze the relationship between a binary risk factor and a binary outcome. There are different types of chi-squared tests. But by far the most common one is the one I just showed you, that O minus E squared over E, that x squared value. And in this case, you get a p-value of 0.50. But notice it gave you a warning. It says 25% of the cells have expected counts less than 5. Chi-squared test might not be valid. If we go back to that table, whenever you have an expected cell count that's less than 5, in this case, 1 out of the 4 values are less than 5, that's 25%, it's going to give you a warning. Because this chi-squared test is not very stable and somewhat might not be appropriate when you have very, very small data sets. Small data sets need to have small people in rows, in at least one of the rows, and small people in at least one of the columns of that table. So when you calculate these expected cell counts, go back to the general form, by taking row total times column total divided by gram total, some of these numbers might be small. Why is that bad? Because when you calculate x squared, notice you're not just looking at the distance between the observed cell count and the expected, but you're also dividing by the expected cell count. And remember, when you divide by a very small number, you get a big quotient. And what you want to do is avoid having cells that have very little information in them, very small expected numbers, because the corresponding rows and columns, they themselves have small numbers of people in that row and column. But that number, that expected number, is going to have a big influence on the value for x squared. So for small studies, the reason we don't want to use a chi-squared test statistic is because we're afraid that the cell for which we have the least amount of information has the smallest expected cell count, and have the biggest influence on the value for x squared because we're dividing by it. So what do you do in that case? That's what SAS is warning you here. is when you have a small study like this, small expected numbers, and this is just a rough rule of thumb. If your cell counts are less than 5, that means it's small. For the expected table, not the observed table, but for the expected table. In that case, the recommendation is use a different type of test of significance called an exact test. And formally, for a 2x2 table, it's called a Fisher exact test. And SAS and other packages will also do that. It's another way for calculating p-values. In this case, we get a p-value that's also very large, 0.6699. It's different from the 0.5051. But for large studies, lots of people, chances are the p-value from your chi-squared test and the p-value from the Fisher exact test are going to be very, very similar. So you can use either. Only when you have small studies, you want to avoid using the chi-squared test and use the Fisher exact test instead. So that's how you analyze the relationship between a binary risk factor and a binary outcome in terms of tests of significance. But what about the other way you can draw statistical inference? You can build a confidence interval. A confidence interval is a range of values built around your best guess, your best risk ratio, your odds ratio from your table. The width of the confidence interval, lots of people, lots and lots of outcomes. Your confidence interval is going to be very tight, as they were in that randomized trial. If you have very small studies, your confidence interval is going to be very, very wide. So, but in any case, the values in that confidence interval are the statements, the hypotheses that are supported by your data set. So, unlike focusing just on the null hypothesis and asking, does your data support the null hypothesis, confidence interval is giving you a wider range of conclusions. It's saying whether your data supports not only the null, but what other values might it support, namely those values which are contained in that confidence interval. I'll show that by an example. So let's suppose we have a 2x2 table. Let's suppose we're calculating the odds ratio, but the relationship between the exposure and the outcome. The exposure, again, might be people who received an intervention. The non-exposed people might be people who received a placebo. The odds of developing the outcome in the intervention group would be A divided by B. Odds of developing the outcome in the non-intervention group would be C divided by D. And the ratio of those two odds that we call the odds ratio. Well, mathematically, that's nothing more than multiplying A times D, dividing that by B, and dividing it by C. Numerically, that's another way to calculate an odds ratio. Well, how do you build a confidence interval around an odds ratio? Use something called a sampling distribution. What that means is you imagine doing many studies just like the one study you did, using the same types of people, using the same numbers of people. So a sampling distribution describes what you'd expect to observe if you could do your study over and over and over again. Sample different people just like the people in your one study. Sample the same numbers of people just like you did in your one study. But see how the results from those many, many studies vary from one another. What a sampling distribution, say, for the odds ratio means is what you'd expect from studies like yours